Welcome back to all after tea break. Now the session will be taken by Professor Susovon Samanta sir from NIT Rourkela on the topic MPPT algorithms. Professor Susovon Samanta received the ME degree from the Jadavpur University, Kolkata, India in 2003 and the PhD degree from the Indian Institute of Technology, Kharagpur in 2012, both in electrical engineering. He is currently serving as an associate professor with the Department of Electrical Engineering, National Institute of Technology, Rourkela. His research interests include analysis, modeling and control of power converters used in photovoltaics, electrical vehicles and space application. Now I would like to invite Professor Susovon Samanta sir to give his lecture. Sir.
Okay. Thanks for the introduction. I cannot see the online participants, no? Okay. Okay. So the topic is very common, and everywhere, wherever you want to include renewable sources like PV and wind, you need to order fuel cell also. These MPPT algorithms are you need to use the MPPT algorithms. So mainly I will focus on the solar application, PV application. And I try to make it very simple. Mostly without any mathematics, just the basic logic and the sense. I hope that you can understand. So the contents is first I will explain about the PV cell panel or array modeling. Then when you connect different varieties of load to the PV panel or array, how you can choose your operating point, or how the operating point is decided, that I will tell you. Then because the full form of MPPT, I think all of you know, is maximum power point tracking. So for maximum power to extract maximum power from the panel, the general rule is source resistance or impedance should equal to the load resistance or impedance. So this is the very simple logic, and based on that, this logic only we will try. So if I directly connect the panel to the load, then depending upon the behavior of the load, operating point is decided, and that operating point may not be the maximum power at the maximum power. So we need some kind of circuit in between load and the PV panel, such that we can change the resistance or impedance seen by the PV panel. So this is the main important point. Then I will just explain about different maximum power point techniques that is available, but obviously it is a is there are so many, but mainly I will concentrate these two algorithm, the P&O and INC. It is like uh, if you see the control system book, they are saying that 90% of the controller used is PID. So in the similar manner, you can say that almost in industry, MPPT techniques algorithms, widely used algorithms are either P&O or INC. And I will show you the difference also. Then I will focus on the limitations of this algorithm, the fundamental algorithms. And there are few limitations. So, and the corresponding solution for those limitation that I worked on. So that I will explain. So this is all about this lecture. Now there is no point of explaining each and every slides, because as I told you that either solar PV system can be it can be directly connected to the grid, or it can be a standalone system. So for directly either, so you need always, so this is the panel, then you need some kind of converter which gives to the DC link, then DC link to three-phase inverter, and it will be connected to the grid. And there are other standalone system where grid is not there, battery is used as a backup. Now all these slides I will skip. So I will come back to this slide. So this is a single diode. There are multiple model available in the literature, but I will explain only the single diode model of the, and this is like this can be cell, or basically number of cells connected in series or parallel creates a panel. So then it is panel. Oh, sorry. So it is very difficult. Yeah, there is always a delay. So panel and then array. So number of panels connected in series and parallel will create array. Now this model, this is called single diode model, and this is the irradiation that is going to the surface of the panel, and due to that this is the current source representing the current source, and it has a PN junction, so that creates the diode characteristics. And if you combine this, then you will get this IV characteristics. Obviously, it is considered, this characteristics is basically there is a extension here and there is an extension here. But if you use the series diode and the bypass diode, then it will be only in this coordinate where the solar panel is actually giving you the power. And this now the panel. So for ideal panel, we are not considering this series resistance or the parallel resistance. So this is shunt and this is series. So if you make this is 0 and this is infinity, then it is a single diode model. But in practical, there is a junction resistance, there is a wiring resistance when you are connected the cells in. So there is always some series resistance existed. And also due to the leakage current, because there is a leakage current which we are actually representing in terms of the shunt resistance. So this is not the actual resistance, but representing different properties of the solar panel. Then, so this one I have already written. So this is the VI characteristics of this solar panel, if you consider NS is the number of series that is connected cell and NP is the number of cells connected in parallel. Now there are 3 points which are important. One is this point, another is the this point and the maximum power. So these 3 points are important. So if I consider, then this is about short circuit current. So in the short circuit, so at this point, if I put V is equal to 0 here, then what I will get? I will get this expression. So from this expression, it can be seen that because RS, this is a shunt resistance, which is basically a very high value. So this quantity and this quantity, the second and the third quantity, is very less compared to this quantity. So from there, actually, what we can assume is that the panel current is mostly proportional to the irradiation. Okay, so this is one of the point. Another point, so that is the short circuit point. So current is proportional to the irradiation. Next is the other point. Other point means where the current is 0. So in the same expression, if I put current is equal to 0, then I will get this expression where we can assume here also it is not exactly, but approximately this VOC is proportional to this thermal voltage. This thermal voltage is also depends on the temperature. So open circuit voltage, in that sense, we can say that open circuit voltage is proportional to the temperature and short circuit current is proportional to the irradiation. So then I plotted for a 100 watt SUCAM panel, which is actually there in my lab. And from here you can see that when we are changing the irradiation, then the current is almost proportional, but not the voltage. But there is it is not that the voltage is constant. There is a variation in the voltage. And if I make the irradiation constant and vary the temperature, then there is a variation in the open circuit voltage. Although there is a variation in the short circuit current, but that is very nominal. So now what will happen if I connect directly a panel or array or a cell to a load? Now, depending on this value of the load, because this is IV, okay, and so 1 by RL, because this is I by V, this is basically okay. So this is I by V. So it is not a resistance, it is basically the conductance. So this slope, so if I take RL and if I invert it, I will get 1 by RL, that is basically nothing but the slope of this load line. So depending on the RL value, wherever it will cut, that will be the operating point. So if this is my RL or load line, and at this point, if it is operating at 100 watt per meter square, so it will operate in this point. So that will obviously not give you the maximum power. So we don't have any control. We can only control by the load, controlling the load resistance to get this value, and that is what we will do that is the basic of MPPT algorithm. Now, if you connect directly a battery, so I just wanted to explain different load. So if you directly connect, so battery is a constant voltage. So depending on the battery that you are connected and depending upon the panel that you connected with the battery, so this will be the operating point depending on the different irradiation. So here also we don't have any control. So the control is there only if I choose a battery which is the voltage is exactly equal to the MPP voltage. But that is possible only for one of the irradiation, but if irradiation changes, that MPP voltage is also changing. The next is battery. In general, battery we are model because battery has a loss. So in general, we are model battery with a internal resistance. That is the R battery. So now what will happen is that previously it was a constant, but now there is a loss. So this voltage plus this voltage should be provided by the panel voltage. So obviously it will be, because see, it is charging. The panel is charging the battery because it is not possible that it will discharge. Then this load line will be different because load line will shift it to the right hand, because this loss, it will carry this loss plus this battery should be PV. So now the voltage should be more than the previous case because it should include this. And if it is, the battery is discharging, then the slope, this curve will be in the left hand side, not in the right hand side. So here also, with the depend on the battery value and this internal resistance, the operating point will be decided. Now nowadays it is very popular to directly connect a panel with a pump. So the pump, what is, because we know this the load torque, if it is a DC motor, so the, or any motor, load torque, the electromagnetic torque should be equal to your load torque. And if it is pump, then this load torque is proportional to omega square. No, this should be TL. This should be TL. Should be proportional to the omega square. And what about TE? TE we know proportional to the IA. Okay. So if I want to derive a relationship between IA and VA, then T IA and omega, from the back EMF we know that omega is proportional to the voltage. So if you replace these three equations, you will get a relationship IA is proportional to the armature voltage VA square. So it's a non-linear. So this will be the corresponding curve. Maximum power if you want at any point of time. So what we need to do is that we need to electronic circuit between the panel and the different loads that I discussed. So this is already I told you. So the first basic thing that you can do is that you can connect a switch series with the load resistance. So as I told you, my main purpose is to the panel, the resistance seen by the panel should vary, should not be fixed. And I should have a control to vary this load resistance seen by the panel. So in this structure, in the circuit, what is the average current? So we know that because this is the impedance of this capacitor is 1 by j omega c, and if this switch is operated with high frequency, then this omega will be high. So high frequency ripple will be passed through this capacitor, and DC will come from the PV panel. So this will be the switch current. So the average value of the switch current should be given by the PV panel. Okay. So this is the normal. So this is switch current. If you do, so this is one cycle. If you do the average, you will get this one, BPV by RL into D. So this should be equal to IPV. So BPV by IPV is the resistance seen by the PV panel, RPV. So that is RL by D. So now by changing D, we can vary the RPV. So that was the point. So this is, but there is what you can see is that load resistance current is very fluctuating. So that is not in proper application. We don't want to change the load current from very zero value to high value continuously. So this is the drawback. Another option is just you connect the load resistance parallel switch. This is like, that was like output filter, and this is like input filter, because the inductor is connected in series. Here also, if you see, so now the RPV, here it is a parallel. So the panel voltage should be the average voltage, should provide by the panel. Previously it was the average current should provide by the panel. Now average voltage should be provided with the current, because of the inductor current is already smoothed. So that is not a problem with the current. So this is RPV. Now this is another relationship where actually we can change, but here also load voltage is continuously switching. So that is also not a very good option. So the options people are using is different converter architecture. So what will happen if I connect panel, in between panel and a load, a buck converter? And I hope that all of you have basic knowledge of converter. I will not go any deep. This is a very simple expression. So this is the expression for buck converter, that output voltage V0 is D into V in. Here V in is nothing but your panel voltage. So from there I can write VPV is equal to V0 by D. So what is the resistance seen by the panel? It is voltage divided by the current. So VPV by IPV. And if I consider a lossless system, so whatever power is generating here, the same power is transferred into the load, then I can tell that VPV IPV is equal to your V0 I0. Okay. So VPV V0 we know. So we can also get the relationship between IPV and I0, which is just the inverse relationship. So you see VPV is V0 by D and IPV is I0 into D. So V0 by I0 is nothing but your load resistance, because this is V0 and this is I0. This is your I0 and this is V0. Okay. So this is RL by D square. The interesting fact is that, so how much RPV we can change, how much resistance we can change, that is seen by the panel. So obviously it is a converter, so the duty can be vary at most between 0 to 1. So minimum is 0 and maximum is 1. So if I put 0 here, so what I will get is that I will get a infinite resistance seen by the panel. Infinite resistance means in the IPV curve, infinite resistance means your current is 0, because it's infinite open circuit. So current is 0 means the line will be here. So this is be the line for D is equal to 0. And the maximum is D is equal to 1, where RPV is equal to RL. So this is basically 1 by, this all lines are, as I already mentioned there, 1 by RL line. So here also, depending on the RL, you have the other end of the curve, okay, intersection point. Now, it may so happen that if D is equal to 1 and you connected some RL, then this RPV is less than the maximum power point, then whatever algorithm you will use, you will never get the maximum power, because if you use the buck converter, it will intersect the point in the lower half of the IV curve. Okay. So because in some time students are asking that I am not getting MPP because of your load resistance, you are not properly chosen your load resistance if you use a buck converter. What will happen to the other popular circuit, that is boost? The same derivation. It is you also know that this is the boost converter input output relationship, and if I do the same analogy by making that efficiency of the circuit is 100%, then I will get this relationship. Here also D will vary most from 0 to 1. So at D is equal to 0, what I will get? I will get RPB is equal to RL, and D is equal to 1, I will get 0. 0 means RPB 0 means it is resistance 0 means short circuited. So it will start. So it will start from here, any point. That point is actually again depends upon the value of RL, and then it will ends at here at D is equal to 1. So if you use a boost converter, then you will get the upper half. Again, there is a problem that if you have a lower insulation level, so it may not possible that you will never get extract the maximum power point, whatever algorithm you will use. If you choose the RL not according to the panel characteristics. So then this is mostly used in all the optimizer that is available in the commercial solar optimizer. So this is kind of a buck boost, or they are also using flyback, because flyback and buck boost are the same input output relationship. Flyback they are using because it has the automatic isolation between the input and the output. This is the relationship. And but now the panel resistance is basically depends upon this relationship. Now again we can check that D is equal to 0 and D is equal to 1. So what will happen? D is equal to 0 means RPB is equal to infinity. So it's open circuit, so it will start from here. And what about D is equal to 1? D is equal to 1, 0. So it is short circuit, so it will end here. So you will see it will cover the full range of the IV curve. So it is not depends upon the what RL value you are choosing. So if you use this structure, any RL value, you can actually extract the maximum power. So this is about the, so all the converter which has this kind of relationship, you can get, you can extract the maximum power. It may be Sepik, Chuk or flyback, all are having this relationship. Okay, so this is already I explained. This is okay MPPT, and now what we can do is basically I tried. We can also consider efficiency into the factor, because it is not that it is 100% efficiency is existed all the time. So if you include efficiency of the converter, then there will be slightly change in the. So these all are PV, okay. Because I prepared the slide at the last moment, so there are some notation are used different note in different places. So now you see this is basically same RL by D square, but there is a efficiency factor. Okay. Now there are, as per my knowledge, there are n number of MPPT algorithms. Okay, there are so many papers on MPPT algorithm. But as I at the beginning, as I told you, that I will mostly explain these two algorithms which are widely used in the industry. Okay, so fractional open circuit, and there are two basic algorithm are there, which is basically fractional open circuit and the fractional short circuit. You can very easily understand that from the IV curve. So this is your VOC and this is your ISC. So suppose you buy a panel and you draw the IV characteristics for different insulation level. So at any particular insulation level, you will get this IV curve. And this panel VOC voltage is basically, it is written in the panel datasheet. VOC, ISC and the MPP at STC condition. STC means standard test condition, which is nothing but your 1000 watt per meter square 25 degrees centigrade. So this VMPP is nothing but a fraction of the open circuit voltage. Okay. In general, it is varying between 0.75 to 0.82 or 0.83. That depends upon also the aging of the panel. So if you this fraction, if you put this fraction there, and if it is matching the fraction or not, accordingly you can change. Another one interesting point I did not mention previously, I should actually mention, because that is required to understand the logic. Yeah. So in all the one thing common, you see that if I will start, obviously d is equal to 0 and d is equal to 1. So what is happening, that if I increase the duty ratio, panel voltage is decreasing. This is very important to understand while writing the code or writing the algorithm. Every case you will see, if I increase the duty ratio, panel voltage will decrease. So this is for buck. See, in the boost, d is equal to 0 to d is equal to. So if I increase the duty ratio, panel voltage is decreasing. Similar to say similarly for buck boost also, d is equal to 0, d is equal to. So if I increase the duty, panel voltage is decreasing. Okay, so if I need to increase the panel voltage, I should do the opposite thing. I should not increase the duty ratio, I should decrease the duty ratio, and vice versa. So this is important to understand. Then where I was, okay, I was discussing about this one. So you just put some fraction here. So for this fractional open circuit, what people are doing is that they after each year or 6 months, they try to find out the characteristics and they try to see the relationship between VMPP and VOC, then put this value here. Now you are checking whether your panel, and you are measuring the sensing the panel voltage. You are checking that panel voltage is greater than MPP voltage or not. So if the panel voltage is greater than MPP voltage, so maybe let us consider that panel voltage is here. So what you need to do? You need to decrease the panel voltage, and to decrease the panel voltage, what you need to do? You need to increase the duty ratio. So that is why you are increasing the duty ratio. And if it is not, so either it can be left hand side or right hand side. So there are two cases only. Either the panel voltage, instantaneous panel voltage, is greater than the MPP voltage. MPP voltage already we have decided, or it is less than the MPP voltage. And wherever it is there, if it is here, you should decrease the voltage. If it is here, you should increase the voltage, and accordingly you should change your duty ratio. So similarly, short circuit current, this IMPP current also some fraction of the short circuit. So same way here, you are only sensing the current and checking, and accordingly you are deciding. Yeah, now the main point. Okay, so this P&O or INC can be implemented in different way. Okay, so mostly in this lecture I will concentrate on this, and at last I have given. So there are basically, it is called direct duty ratio, where I can control the duty ratio, and duty ratio can be controlled in this fashion, or this can be a constant. Okay, this can be a constant delta D, or it can be a variable delta D. So there are many papers that work on this variation called adaptive duty ratio control. So this is one of the way where there is no control loop. It is like open loop control. We are just changing the duty ratio and the panel voltage is changing. Another way to make it a closed loop, what people are doing is that so this sensing the voltage. This is called VREF control, voltage reference control. Sensing the voltage, okay, and giving to the MPPT algorithm, either P&O, INC, whatever algorithm. Then you generate the reference voltage from there, and you compare the instantaneous voltage with the reference voltage, and then you use a PI controller, and then duty ratio. So previously this part was not there. Directly duty ratio was generated from here and given to the gate of the switches, converter switches. Now you are not doing that. You are making a closed loop. You are trying to compare with the instantaneous PV voltage and use a PI controller, then giving the duty ratio. So this is voltage ref control Similarly, you can do the current reference control. So in the current reference control, you are generating not the MPP voltage, you are generating the IMPP current. Both you can actually generate and comparing with the current and then the same thing. Okay, so two things important while going through the this lecture. I will more clearly I will tell about this one. As I told you, one is this delta D. There are many researchers actually worked on this delta D. And another is the perturbation time. Perturbation time means how much interval you want to vary the delta D. Okay. So this delta D, depending on the delta D, if you, so this is my IV curve, and till now I have not shown the PV curve. I will show later on. So PV curve is basically if you multiply the voltage and current each and every point, you will get the corresponding PV curve. Okay. So what I am telling is that, so in case of delta D, so you are actually from one point you are moving to the another point. So how fast you want to move, that depends upon how you are choosing this delta D value. If you choose delta D very high, it will from this point to this point it will reach very fast, but it will oscillate around this point in a larger amount. So that is the problem. And if you choose small delta D value, then it will from this point to MPP point, it will take more time to reach, but here oscillation will be less. Okay. And the perturbation time means how much time interval, how much time you want to change this delta D value. So as I told you, it is like, if you think about it, it's like an open loop system. So you are giving a disturbance delta D, okay, and then the panel voltage will change. And panel voltage is connected with a converter with a load, so it has its own dynamics. So all of us, we know that if I give a disturbance, a control input, step input, then obviously this panel voltage requires some time to settle it. So the time so how much time interval you can also understand from here, that how much time interval you want. You want that after giving a delta D, this VPB should be first settled before giving any another control input. Okay. So that is why this perturbation time is depends upon the settling time of the system. So it should be always more than the settling time. You should first settle the system and then only you should give the next delta D variation. Okay. So what is the time? How much time I have? Okay. Time. So what is the algorithm? First, let us understand about the P&O algorithm. So this is your PP. So this is the MPP point, and there are two sides. Left hand side, right hand side. It is also called hill climbing. Like while you climb a hill, how you climb a hill? If you think, if you are if some blind person is try to climb a hill. So what is the logic? Logic is that in the left hand side you will see the slope is always positive. Now let us consider two cases as for the arrow direction. So if I am here and I reached here by walk. Now from here to here your power is increasing, your V is also increasing. So del P is greater than 0 and del V is also greater than 0. Okay. So the slope is positive. Now think, because you are a blind person, you don't know. Now see, you are moving in the opposite direction. So what is happening? Your del P is less than 0. and your del V is also less than 0. So both are negative. So again the slope is positive. So in the left hand side always the slope is positive. This is one point. And right hand side the slope is always negative. Okay. So that also you can check from these 2 points in both that, because there is only 4 possibilities. Either you can go in the right direction or wrong direction from left hand side, or from the right hand side also you can go to the correct direction or in the wrong direction. Now you tell me that if you are here, so this is only the 4 case that is possible. There is a 4 cases that possibilities are there. So if you are moving from here to here, then if you want to take the decision, so you reached here, now you want to take a decision that what I should do. So obviously you should move in the same direction. Okay. So this is one point. Now if you move the other direction, the opposite direction, what you should do? You should actually increase the voltage. So both the cases in the left hand side, your original decision is you should increase the voltage. Either if you go from this side to this side or this side to this side, you should always increase the voltage. And here what you should do, if you were from moving from here to here, you are going in the correct direction. So what you should do, you should decrease the voltage. And if you opposite, also you should decrease the voltage. Okay, so if you are in the left hand side, you should always increase the voltage. If you are in the right hand side, you should always decrease the voltage. So, and what are the 4 possibilities that I already told you? So based on that, this logic, so you first sense the panel voltage and the panel current. So 2 sensors are required, one to sense the panel voltage, another to sense the panel current. You calculate the instantaneous power, present power. Obviously, if you use a sensor, current sensor, you should not take the instantaneous data, because there are so much noise in the sensor data. There will be too much variation. So better always to take some samples and then average it and then take that as the voltage and the current. So power, and this k and k minus 1 is basically the instant that I told about, that how much instant you want to, how much time difference you want to calculate the panel voltage and the current. So VKIK, and this dp is what? The delta p, basically the variation from this point to this point. So you will get the variation. So now you see it's very simple. You check whether del p is greater than 0 or not. If del p is greater than 0, so it will come here. Now you are checking that whether del v is greater than 0 or not. So del p greater than 0, del v greater than 0. What is your logic? Del p greater than 0, del v greater than 0, you should increase the voltage. So increase the voltage means, I told you, you should decrease the duty ratio. So you should decrease the duty ratio. So basically that means this del p greater than 0, del v greater than 0 means you are moving in this direction. Correct direction, go on. So you increase the voltage. Now the other point is that your del p is greater than 0. Okay. But del v is less than 0. So what is the point? Your del p is greater than 0, del v is less than 0. You just think about it. So if you move from this point to this point, so what is happening? Your del p is greater than 0, but your del v is less than 0. So what you should do? You should decrease the voltage. Decrease the voltage means increase the duty ratio. So del p greater than 0, del v less than 0. That means you are in the other side. So you should decrease the voltage. That means increase. So you should, from these two, actually deciding what side and what direction you are moving. Okay. So this is the 4 cases. Similarly, you can understand that dp del p greater than 0. It's not. So that means del p is less than 0. Del p is less than 0. And if I consider that side, so del v is less than 0. Del v is less than 0. So that means we are in this, we are moving in this direction. So what we should do, we should actually increase the voltage. Increase the voltage means decrease the duty ratio. See, decrease the duty ratio. Okay. So, this one will now the steady. There was animation, so it is PDF. So the animation is gone. Okay. So this P&O on INC is actually operate in 3 state. It is not, because see, the thing is that we always try to, it is like part up the, what is the algorithm, part up and observe. So you first part up and then you observe. So until and unless you perturb, you will not observe. So perturbation should be given to all, should be given always. So that is why. So suppose, see, I want to explain this steady state behavior. So suppose somehow I have taken a decision that I should go from 1 to 2. Okay. And I need to take a decision here at 2. At 2, what is happening? At 2, both power del P and del V both are increasing. So I should move forward. So I should move forward means it should be going to, and I should decrease the duty ratio to increase the voltage. So it will go to 3. Now what will happen? At 3 now I need to take decision. So at 3 what is happening? My del P is, although del V is increasing, but my del P is now reducing because I already passed the peak. So if del P is less than 0 and del Phi is greater than 0, so this will be less than 0. So what I should do, I should actually decrease the voltage. So I should increase. So I will come back to this point 2, and at point 2 what is happening? Del P is increasing and del V is decreasing. So again the same thing. Again I should decrease because this is the decision. Because of that, it will again come back to 1. So it will now almost always you will see a 3 stage behavior around the steady state point. I will show you in the experimental results also that we did. Okay. And now incremental. So P is equal to, we all know P is equal to this voltage and current. Now if you just differentiate with dP by dV, then you will get this expression. And at maximum, to have a maximum, your slope should be equal to 0. So at maximum power, this di by dv should be equal to minus I by v. And to the left, this di by, now see, this is now like, this is your IV curve. This is your IV curve. Now one point you can understand that every time if you just try to calculate incremental conductance, not the resistance, conductance. So see, if I am here, if I move from this direction, always your current is decreasing. Okay, and voltage is increasing. So as the current is decreasing, so this del I by del V is always a negative quantity. Okay, and you are checking that is equal to greater than IV or less than IV. Now, one thing you can understand. Again, there is one part which is left hand side. There is another part which is right hand side. So what happened to the left hand side? See, delta I variation from this point to this point, because it is a short circuit. So current is almost constant, decreasing, but decreasing very slowly. So this del I by del V, if you see from incremental conductance point of view, del I variation is very less in the left hand side, but del V variation is high. So if this quantity, the incremental conductance quantity will be very small in the left hand side. What will happen to the right hand side? If you see in the right hand side, it is basically, it is called, this zone is called constant current zone and this zone is called constant voltage zone approximately. Now here from this point to this point, current variation is more than the voltage variation. So your numerator value is more than the denominator value. So this value will be more. So that according to that, you should check this one, whether it even in the left hand side or in the right hand side. Now this is the algorithm, incremental conductance algorithm, but it is theoretically okay. Many papers is actually initially they claimed that this INC algorithm is better than the P&O algorithm, but later on they actually proved that both the algorithms are almost same. Now what is the difference? So this part is almost same, left part that I will discuss. Only thing is that dv is equal to uh, 0. Now these two condition is actually never happened. See, del v, because we are perturbing, so del v is in practical sense never equal to 0. So this condition you will not get this condition. Okay. And similarly, this del v di equal to 0, this del I equal to 0, this condition is also not possible. So in this incremental conductance algorithm, what we observed is that some of the conditions is given, but these conditions, the loop will never go to those conditions because those conditions are not practically happening. Okay. So ultimately what is happening is that this case, because this is also not possible at MPP. So you are only checking that your incremental conductance value is greater than minus I by V or less than I minus IVV, and then accordingly you are either decreasing the duty ratio or increasing the duty ratio, because based on that you are in the left hand side or right hand side. Okay. So this is the advantages of this one, these two algorithms, very simple and easy to implement. But these are the problems. What are the problems? This tracking speed is slow, means if you use a fixed duty ratio then it is slow, or rather than I should say that how to choose this delta t is also a very important factor. Then I will show you that there is a problem exists in both the algorithm, which is called drift. Okay. And another limitation of this two algorithm are they have a steady state oscillation. So around MPP there is a oscillation, but what you want is the algorithm, once it reaches near to the MPP, should be stopped. Okay. Then it can always extract the approximate maximum power. Okay. So these three are the problems. So I will try to show you the solutions of this problem also. Okay, one by one. So first I will explain about the drift problem. Yeah, drift problem. So what is drift? Suppose I'm already, I will explain here in this point. So you are operating. So suppose you are operating this 1 to 2, 2 to 3, as I told you in steady state. In steady state you are operating. Now suddenly there is a change in the irradiation. Okay. So you are operating here. Suddenly there is a change in irradiation. So what will happen? So if you are connected a load, so it will be like it will be operating. My drawing is sorry, my drawing is confusing, so better to erase it. So what I want to show you is okay. So what will happen is that if it is operating, previously it was operating in the near equal to MPP. Now due to this increase in the insulation, it will come here, because your duty ratio is at that time, because it is, if you see the buck converter is RL by D square. So D is not changes instantaneously. So instantaneously irradiation is changing. What will be the operating point? In the new curve, the operating point will be this one. So now see, It was operating previously with this irradiation value, this PV curve. Now irradiation is changing. So this will be the new irradiation curve, but your duty ratio is not changes, and the load resistance is not changing. Okay. So what will happen? It will come back. It will be the new operating point before any decision will be this point 4. So if it is going from 1 to 4, what is happening? 1 to 4, your del P is greater than 0 because power is increasing, because it is your irradiation is increases. Irradiation increases means the power will increase. And what about voltage? Del V is also increasing from this point to this point. So as for the Piando algorithm, what should be the decision? Del P greater than 0, del V greater than 0, I should increase the voltage. So I should increase the voltage means it will come from this point to this point. But actually what it should do? You should actually decrease the voltage. But due to the Piando algorithm, it is increasing the voltage, because the Piando algorithm does not have the knowledge that the changes in the power is due to the delta D variation or it is due to the irradiation change. It does not have that knowledge. So that is why it is taking a wrong decision here, because we know that in the basic Piando algorithm, if del P greater than 0, del V greater than 0, it should always increase the voltage. Now we have also checked this one. This may be a dangerous thing. Now, so from this picture to come to this picture, so initially it is changes to this, and when it is here, okay, it will come back at this point, and at the same point, whenever it is come to this point, taking wrong decision, again irradiation changes. So it will shift to this point, and then what is happening? Again del P greater than 0, del V greater than 0, it will come back to this point. Now if you think that at this point again power irradiation is increases, then it will come back to this point. So like this way, it may happen that it go to the open circuit voltage. Okay. And this problem is called the drift problem. Now, actually, with my first PhD student, we worked on this this problem, and it was published in Industrial Electronics, and you can see in the Google Scholar. Actually, till now, it is more than 500 citations as per the Google Scholar. So what we did, we did nothing basically. We just wanted to put some condition such that the algorithm have the knowledge that, as I told you, that this power del P variation is whether it is due to del D variation or it is due to the irradiation change. And how you can, so that is also very simple logic, how you can check that your increasing del P is due to del D or irradiation changes. So if you see the IV curve, so in the same IV curve, in del D variation, we are actually operating in the same curve. So always, if I increase the voltage, if you see the del I is less than 0, or I already told you, and del V is greater than 0. Okay. But if there is changes in the irradiation, then del I is greater than 0 and del V is greater than 0. So he puts one extra condition here just to check that the del P variation is due to the del D variation or due to the irradiation change. Very simple. You just check it here that, so dp del P greater than 0, and remember, as I told you, this drift problem is only for increasing insulation. It will not happen to the decreasing insulation. That also you can check yourself later on. If you find any difficulty, you can also solve that problem easily by yourself, that why it is not happening in the decreasing insulation. Now see, now del P greater than 0. So means either there is a change in the delta D or there is a change in the IPH, irradiation change. How to decide? What is there? So check you check dV greater than 0. Okay. Now dV greater than 0, del P greater than 0, del V greater than 0. That is also possible for del D variation. So till now no conclusion. But del P greater than 0, del V greater than 0, and del I greater than 0 only possible if there is irradiation change. Otherwise, if it is in the same curve, del I cannot be greater than 0. It is, as I told you, it is always, because you can see, always del I should be less than 0. So other than these two conditions, if you just check in this loop only, so that is why I put this in this loop. In this loop, it is not there because this is decreasing insulation loop. So del P greater than 0, del V greater than 0. If del I greater than 0, then I know that this is due to the irradiation change. And as this is due to the irradiation change, I should what? I should not increase the voltage. I should basically decrease the voltage. Decrease the voltage means increasing the duty ratio. Okay. And if dP greater than 0, dV greater than 0, and di less than 0, that means it is due to the duty ratio. So I should do the same thing. I should increase the voltage. Okay. So this is the small modification that we did, and then actually it was accepted at the first review itself. So then they told us to do some kind of mathematics. Mathematics means just to show that due to, when there is a change in the irradiation, you should show that your del I, like di by dg, this is basically the insulation, should be greater than 0, and dV by dg should be greater than 0. So they told us, and we did with the equation, solar panel equation that I discussed. You people also can check from the solar panel equation. This was the equation. Okay, and we put this expression, and we just got this dPV by dg and di by pv dg. So there are all the equations are there. I don't want to go. I just wanted to say you about the logic, and you can prove that when there is a irradiation change, voltage will increase, current will increase mathematically also. But logically, you can understand that is always, that should always be. Okay. So same thing is happening in the incremental conductance also, and we put the same thing, nothing else, just to check that the changes in the incremental inductance is due to the same curve variation or due to the irradiation changes. Okay, so this was the setup long back around 2014 or 15. We used this epic converter, okay, with a 40 watt panel, and we just try to extract, because it was the incandescent lamp was there, so it was also not properly placed. So maximum power we extracted about 16 watt, if I remember correctly. Okay. And maximum irradiation we got 480 watt per meter square, just for that lamp arrangement. But if you use LED lamp nowadays, if you use LED lamp, you will get better value of this irradiation. But obviously, if you put the lamp, the another problem is that your temperature of the panel will increase. Okay. So I have some interesting results here. You can see. So this is, as I told you, this is the 3 stepping. So see, so it is that 1 to 2, 2 to 3, and 3 to 2, 2 to 1, like that. So it will from here, it will come back here, then it will go. So you see, this is voltage. So voltage is increasing, then it's decreasing, then it decreasing, then again increasing, then increasing. So 2 increasing, 2 decreasing. If you see that 1, 2, 3, it is like that way only. Okay. Now I told you about the drift. Okay. So we check with two cases. One is fixed duty and one is adaptive duty. Okay. So this is for fixed duty ratio. See, at this point, actually we make certain lamp on. Okay. So initially it was 270 watt per meter square, and then if you on more lamps, it will go to 480 watt per meter square. So now, so instantaneously, this is the power and this is the voltage. Now A is conventional, this is our, okay. So now see the first that's conventional. So this will be the voltage. Now here your program should take a decision. So as for the old algorithm or original P&O algorithm, what is happening? Del P greater than 0, del V greater than 0, it should increase the voltage. See, voltage is increasing. And because the voltage, so it is away from MPP, as I told you. So that is why you see the power is decreasing basically. It is not tracking. Okay, it is whatever it should take the decision, it is taking opposite direction. Now come back to our algorithm, drift-free algorithm. Now see here, it takes, because now it has, it knows that this changes is due to the irradiation changes. So I should decrease the voltage. So it is decreasing the voltage. And so this is the power, you are getting more power than this one. Okay. See, it is 5.3 watt and this is 5 watt. Remember, this is for 16 watt panel and 16 watt. So although it looks like very low, but if you have a huge panel, huge array, then it is significant. And but this decision is only at first point. After that, the first decision is wrong. After that, it will do normal. There is no problem. And this is for adaptive. So adaptive also we saw, if you have adaptive, then adaptive is because of the adaptive nature, it will give less power than the conventional delta T. Okay. Now, so this tested we actually done with the that lamp. But what is in the reality? What is happening in the reality? Sun is not suddenly totally dark and totally illuminated. It is not like that. So that is why all the MPPT algorithms, if you try to publish a paper or if you try to develop an algorithm, it should be actually tested with this EN 50530 standard. There is a standard for verifying the MPPT algorithm. So what is the standard? It is like the same thing. It is not considering that irradiation is changes instantaneously. It is not. Irradiation, whenever we can also see that it is changes in a slope. Okay. So this is the slope. There are you can see that this part is basically slow variation. Here it is a fast variation. So if there is a fast moving cloud, then you will get this kind of variation. And if it is slow, then you will get this kind of variation. And you should always test your MPPT algorithm with this standard. And according to that, there are two efficiency. This is efficiency of your algorithm, not the converter. Efficiency, there is a static efficiency and there is a dynamic efficiency. Dynamic efficiency is only possible if you do with the EN 50530 test. Because what is the difference between static and dynamic? It is at the particular point, and it is throughout the time interval you tested your MPPT algorithm. Okay. So what we observe, very interesting point, we also mentioned in the one of the paper, that if you test with this EN 50530 so see, this is the so we did that EN 50530 with a slope 50 watt per meter square per second, and this is for results 100 watt per meter square per second. If you see, although if it is a slow variation, there is not a problem. But if there is a fast variation, I told you, see what is happening? it will from here to here it will come here, then here to here it will come here, then again each 100 watt per meter square. See, this is 100 watt per meter square, 200, 300, 400. So this slope is 100 watt per meter square. Means each 100 watt per meter square there is a change. So now, because it taking wrong decision, every time it taking wrong decision, that is why it will stuck to this point. And you are only extracting 20% of the power. So efficiency is very low. And now after that, if you make it a constant, then obviously it will track. Okay, because as I told you, it will only take the wrong decision at very first time. Okay, so that is why you will see it will, you will get a, if you want to test your algorithm with this EN50530, you will get this kind of with a fast slope. It will stuck to this region only. Okay, but this is for drift free. You see, it is continuously tracking. Now there are some efficiency calculation. It is almost all are more than, because it is algorithm only, algorithmic efficiency. It is more than 99 point, and the efficiency is basically the original power and whatever your algorithm is giving you the power. Now another one is, as I told you, another limitation was the steady state oscillation. I already told you this steady state oscillation. So what is steady state oscillation? This is also idea is very simple. So steady state oscillation is basically, as I told you, so voltage, this is your voltage, this is your voltage part. So voltage is first increasing, then decreasing, then again decreasing, and then increasing. So this is one, this is another, this is another. So if it is reached the steady state, we know we should have this kind of behavior in the steady state. Okay, in steady state, three step behavior. So by seeing the waveform, actually you can tell that whether the algorithm reaches the steady state or not for this P and O and INC. How? So you check, you just compare this voltage value and this voltage value. Okay. So this two voltage value will be, if it is less than some tolerance, there is some variation, but if you see it's very minute, there is a variation obviously, but this V at A and V at C, if I subtract VC minus VA, I will get some, and if it is less than some value, that value actually you should decide after doing some experiment. So this value is very near, this value and this value is, so difference is very small, and this voltage is greater than either of VA and VC. Now see this circle, what is happening? This voltage and this voltage is again very small. The difference is very small, and at the voltage D, this voltage is lower than either of this voltage. Okay. So if I check this 3 voltage, okay, I put a counter. I keep a counter in the algorithm, and I'm just checking 3 voltage level, first, second, and third. And if I subtract the first and third, checking the difference, is very less or not. And voltage is better than this voltage now. If it is yes, I have some sense that mainly the steady state, but not to be more. But you should do whether it is reached or not. We are making the now we are taking this voltage and voltage and checking this and whether voltage is less than that or not. If the equal was 0, that is the steady state. And if it more conduction plus, and if this continuously state is something like that, say that this is steady state. If it is less steady state, what I should do? To stop the operation. I will not terminate to the operation and operate in this point. But what D I will get at that point, I will operate at that D only. Okay. So now this is the algorithm to steady state operation. But we may ask that is only if it is operating the same insulation. So if there is insulation change, then what will happen? Should actually again start down. So for that, we I told you about the difference. So whenever there is insulation change, you know del V and del I both are zero. So if you change this and also the del V is greater than zero, how much? And del I greater than zero. There, then irradiation to I should come out from this session. I will start in one second. I will take this. Okay. So price in hostel energy, the same thing that we do, I can explain it uh, here. But I told you that I will check these two level. So if I start this is A, so this is minus 1 and this is A minus 2. So I'm checking the zero magnitude. I'm giving it to giving some tolerance. I'm thinking that value is less than some tolerance or not. This tolerance value also depends upon condition level changes. That do actually do one tab. Even you should have proper care of the panel that you use. Then I'm it's or we want. Okay. So if it is, then we can variable identity meaning that identity will make identity is equal to 1 and I will start counting. Identity means I hint that it is predicted. Then I will start here. So this is 0 and 1 and 2. So I will B3, B4, B4, B5. Now check this error. I will check whether it is less than D1 or D4 is less. So if it is I told you, we are almost guaranteeing that it is steady state. So I will make in 1 and now count is for the 0, 1, 2. Again, we will make another cycle for 2, 3, and 4. So count is 4. If I this three value, and I will check, and then I will make another variable that if I is equal to 3, basically you is the steady state. Okay. And then you use the same as this value that will do the near MPP, not actual MPP of the battery, because it's a content part, so you will do the actual MPP. This is we are with the district load as well as the battery load. So you can I can explain this point diagram. Okay, this is resistive load. You see at this point, actually, if I start at this point, I know that these value and these value, these two value are almost basically we are taking yeah, this is another point we are checking that value. So that means we will check this value, this value. So these two value very very low, and in between value voltage is greater than any of the voltage. So your identification will start. Okay, and start from 0 to 2. So see, so from here, so it's 0, 1, 2, 3, 4. Now from here you see there is no oscillation. There is no switch oscillation. Similarly, we can take from here, from the ILC also. And there is we incorporate shifting condition also if the irrigation is changes not. So when the irrigation change, so it will again come back to the normal MPPT algorithm. So function is paper. I'm not included, but this is the basic this, solution. Okay. So this is the last thing I want to explain about the database control. So as as I told you that it is it's closed loop. So you need to design a PI or PI controller for that. For controller design, you need a transfer function. You need a PV panel voltage to DP transfer function. So that means transfer function means only the output. What is your output? Your output panel voltage. If you see the DP, how much panel voltage you change, that is do. Okay. So, but it's a nonlinear uh, element. So the characteristics is nonlinear. So usually is in linear around, so any linearization is the operating point. So this MPP operating point, and this line. So you know this equation, okay, and this MPP and if you know that and you can actually find out the linear equation. You can find out the equation. Slope, we know this is the slope. Okay. And another point, VMP is IMP. So slope and uh, this point. So this y minus y1 is your slope into a minus a1. Is the equation. Where this a is the slope from this point. So to get the slope, just divide by and then operate at IMPT. So you can get note this one you want to think that your DMPP IMPP. So if you find one point, then you can get the linear of the nonlinear panel. Okay. Okay. पहले हुआ था क्या? पहले ना, इसके पहले किसी का लेक्चर में ना।
Hello, hello.
Yeah, sorry for the interruption. So I was I try to linearize this curve. Okay. So equations, panel equations, you already know. We can find out the slope, and as we know the slope and the 2 points, one is BMPP, another is IMPP point. This MPP point. Then I can get the linear equation. Now what I want is that I want to represent this as a linear circuit with a voltage source and a series resistance. Now this equation is this equation. So this equation and these two equations should be equal, and accordingly we can find out the V equivalent and the R equivalent. From there you can actually understand this uh, R equivalent is nothing but 1 by GMPP, basically RMPP. Okay. So GMPP already you can find out from by di by dv by doing the derivative of this equation at MPP point. So you know the V equivalent, you know the R equivalent, and see BMPP, IMPP, GMPP all are available in the corresponding values are directly not available, but you have all these values in the data sheet. From there, actually, you can, for that specific irradiation case, you can find out the what is the V equivalent, what is the R equivalent. And we tested with something with some boost converter with that 100-watt SUCAM panel, and we got this transfer function. So what is, how do you get the transfer function? Obviously, there is another point I should actually mention. It is like, so now the panel is replaced with the linear model, voltage source series with the resistance, and then this is your boost converter. Then you can use any averaging technique, either state space averaging or circuit averaging, to find out this GPV by D. So the same way we did it here, and this was the GPVD, and you can, after that you can there are n number of ways you can design the PI controller. So that is one of the method we did using the frequency specification, frequency domain specification. But the point is not that. Point is what I want to mention is that as we know that in the different irradiation, your V equivalent and R equivalent will be changed. So if the V equivalent, R equivalent is changing in different irradiation condition, that means your system will change at different irradiation. As your system will change, you should actually find out a different kpki value, and we tested it. So this is for, so you see the kp values are not same, because with the different irradiation, because system is changing, so your kpki kd value should change. So is there a way to adaptively change this kpki kd with the changes in irradiation without putting any additional sensor like irradiation sensor or temperature sensor? So that is also possible, that we did in the one of the work. Here what we observe is that there is a relationship between irradiation and the kp value, ki value and kd value. This was the relationship, and this relationship is actually, after doing some calculations, we found out this relationship. And what is, so you know the STC condition, you can find out STC condition is what? STC condition is 1000 watt per meter square at 25 degrees centigrade. Okay. So at that condition, you can find out V equivalent, R equivalent. You can find out kpki kd, corresponding kpki kd. So that corresponding is referred to as kp STC. Okay. And any other operating condition other than STC, how it will change? It will change. You should multiply with a K. What is this K? K is basically STC condition MPP by operating condition power. STC condition power, MPP power, and operating condition power. So that also you can find out, because we are always using voltage and current sensor. So every time you can find out this K value. Okay. And you can do this relationship, use this relationship to changes the PID value adaptively with the changes in the operating condition. Okay. So there are some, so I will directly go to the experimental section. So this is different. So one thing only what I want to tell you is that there is a changes in the irradiation, and this was without the adaptive. So without the adaptive, you see this is taking little bit longer time, but this is with the adaptive, it taking somewhat lesser time. So the point is, as the operating point changes, your PID value should change, and you should find out some way to adaptively changes the PID value. And this is one of the way. There are other ways also you can find it out. So this is all about the lecture.
Now the session is open for discussion. So I request the participants to put forward their queries to sir.
Anyone is having any doubt or any clarification? As usual, no one.
Any doubt can mail to sir.
Yeah,
So
sure.
I would like to express my profound gratitude to Professor Susovon Samanta sir for such an informative and conceptual lecture, giving every basic details of PV cell, PV characteristics, and different types of PV MPPT algorithms, their disadvantages and respective improvisation. Thank you very much, sir. So the next now it's time for lunch break. Next session will start at 3 p.m.